So by now you're probably saying, well, okay, integration, we know a lot of tools, we have a lot of techniques. We'll just find our antiderivatives and life is good, and we're good to go. But there's a question. What if there is no antiderivative? Now you're like, what? No antiderivatives? Well, what I mean by this is that you might have functions which don't have nice antiderivatives. Now, every continuous function has an antiderivative. That's one of the fundamental theorems of calculus results. But there are some where we don't have any good antiderivative. And here's an example. E to the minus t squared. It looks like a harmless function. And it's a very important function, too. If you were to step back and sketch it, what would it look like? Well, it would look something like the following. So this is e to the minus t squared. And this is a famous curve. It's called the bell curve. And in statistics, they study this extensively. And statistics is actually a significant part is built off of understanding this curve, which means you need to understand this integral, but this does not have a nice antiderivative. In other words, you can't write it as some combination of functions that we already know. So to overcome this obstacle, we created a new function which we call the antiderivative of this function, but that's a different story. So that's one thing. We might have a function where we don't know the antiderivative, we can't find the antiderivative. But there's another thing that might happen, which is we may not even know the function at all. So what does that mean? Well, we may just have data. So our data, we're measuring something, and then we have some sort of set here. And we say, okay, well, what's this function doing? I don't know. I don't know the function. But I do know what's happening. I can measure it at different points. And, well, based off the data, we might want to say, okay, what's the total between 2 points? You know, what's the total amount of accumulation? And so we want to estimate this area, which again, is really estimating a total. And in the next part of the course, which is not that far away, we're going to talk about why you might want to estimate it. Of course, this is even more than we might often have. Sometimes we don't even have the whole function. What do we have? Well, what we really have is the following. We have the function at a series of points. And it's doing something. So maybe that's what we have. All right? So in other words, what we have is we have samples of the function. And so we have some data. And what we want to do is we want to try to say, okay, given that, what should be underneath the function? So we kind of like have to guess at what the curve is doing. And so we're going to talk today about, how do we go about doing this? And the answer is, and hopefully it doesn't surprise you, because it's very similar to what we did in Calc 1, is we're going to break things up into small parts, work to understand each part, and put it all together. And so today we're talking about numerical integration, which is just a way of saying, suppose I can't use the function, I don't know the antiderivative, and maybe I can only have some sample data. What can I say about the total? And how can I get a better estimate, a better answer? So that's what we're going to be after. So as a little bit of a warm-up, we'll look at this function. All right, we talked about this integral, 0 to 1 of e to the minus t squared. And here's the graph. You're probably thinking, that doesn't look very bell-like. Well, if you step back, you scale it, it looks bell-like. Okay. So we want to estimate, or as the word says here, approximate. Now, the nice word here is geometrical. So we are going to be thinking about geometry as we go through today. So when we think of geometry, we think of things like rectangles and other flat type shapes. They tend to work pretty well. Triangles, maybe. Well, something. So what can we do? Well, there's some things that we can do. So one of the things we can do is we can just be really simple and say, hey, I can put a little box downstairs. Here's a little box. And I definitely know that the total area is at least as large as this box. Well, the bottom has length 1. What's the height? Well, I'm on the curve e to the minus t squared. This is at t equals 1. So what I can do is that the height would be what happens when I plug 1 into this function. So that's e to the minus 1, or 1 over e. So the area of this thing downstairs is 1 over e. All right, how about the area that's sort of bigger than it? Well, again, I can think geometry. And what I can do is I can put this into a bigger box. So instead of having a box that's inside my piece, I can have a box that contains my piece. So this box would have base 1, but also, if I plug in 0, e to the 0 is 1. So it has height 1. So the area of this bigger box would be 1. So we can combine these two ideas and say, you know, we can conclude the very, very poor estimate, and you'd be surprised how often a poor estimate will do the trick, but it is an estimate, approximation. It's between 1 over e and 1. Now, is that the answer? Probably not. We don't know what it is. We've narrowed it down. This is above a third. That's not great. So what's a better shape? Well, if you look at this, it's a curve, but it's not too curvy. It's, it's not like, wah! It's sort of like, and so what can we do? Well, here's an idea. Let's take this corner and connect it to that corner. And if we did that, we have some shape that looks like that. And that's a nice shape. So what shape is it? Well, it has two parallel sides. The left and the right side are parallel. It has a nice square base. And then there's this other side that's coming in at an angle. So this is called a trapezoid. And so trapezoid you should think of as something which has two parallel sides. All right. Well, what can we do? Well, if you know the height on, say, the left and the height on the right, or the heights are the heights of the parallel sides, and you know the base, the area is that you take the heights and you average them. So like, what's the average height? And then you times it by your base. So in this case, our heights would be 1 and 1 over e. So we could say that an approximation by the trapezoid, well, 0 to 1, e to the minus t squared dt is about, well, 1, that side on the left, plus 1 over e divided by 2, so that's average height, times the base, which is 1. Okay, so it's about 1 over 2 plus 1 over 2e. Now, again, it's an estimate, definitely better than these two estimates because it's doing a better job of capturing the behavior. Is it an underestimate or an overestimate? Well, it looks, and again, we have to be careful here, it seems like we're chopping more off than we're missing, because it looks like we're missing a little tiny piece here, but relatively more here, but not too much. This is pretty decent given how much work we put in. And so, all right, what we want to do is sort of go through and talk about these things, build up these ideas, and see what we can do. Maybe we can do better. So there's more or less 3 levels we're going to go through. So we're going to start at the very basic level, which is going to be a bit of review. And so this goes back to our good old Calc 1 days, where we said, hey, if I want to find an integral, I can think about taking my shape, chopping it up into little pieces, then each piece is a rectangle. Where downstairs, there's not a lot of space, so there's a little tiny bit, and then there's a height. Now the height, you have to think about, okay, how do you pick the height? Well, the answer is you take your curve, and you pick some point in between the left and right hand side of your interval. So I'm thinking of xk and xk plus 1 as the bottom of a very tiny thin strip. And I say, well, there's a couple things I can choose. One thing is I could look at the left hand point. So that says for the height, look at what's the function doing at the left. So you plug f in. So here's our height up here, f of the left point. The other thing you could do is say, well, let's go with the middle point. So halfway in between xk and xk plus 1. So the way you find that point is you take half of xk and xk plus 1. You plug it into your function, and that's the height of your rectangle. And finally, the other common point, now there's many points, but the other common one is the right end. So in other words, you plug xk plus 1 into your function, and whatever that value is, that's the height. So we have these rectangles. Now, depending upon which point we pick, we get different heights. And what's the idea? Well, we're breaking it into little parts. Each part is a rectangle. And really, here's the key. How do we think of what's on the top? So if we look on the top, in each case, it's like we're taking our little strip and we're just putting a flat, constant thing on top. All right, well, that's good. Now, what's the pros? Here's a definite pro. Easy to work with. We love that pro. We want everything to be easy to work with. Is there any cons? Well, it's not always very precise because I'm treating the function like it's behaving like a constant. But most functions aren't behaving like a constant. Most functions are changing. And because of that, it cannot always capture information until you use a lot of sampling, get a lot of points. So let's do our example. And by the way, we're going to keep coming back to this example. So you're going to see this picture a lot of times in the next little bit. So we're going to use the 3 different type of Riemann sums with 2 strips of equal width to approximate the integral from 0 to 2 of 34 over 1 plus x to the 4th. Now, 2 strips, that means we're going to break the interval from 0 to 2 into 2 parts. Now, the other clue here is equal width. Well, from 0 to 2, that's distance 2. So if we would go halfway, that would get us to 1. So there are our 2 intervals. All right, so what do we do? Well, we need to figure out what our estimates are. So again, how do we work? We're always going to have the area is we take a function for each interval times the width of each interval. In our case, because we have 2 strips, the widths are 1. So let's look at what these become. So we have our left, we have our midpoint, and we have our right. All right, so those are the 3. Okay, so let's start. We'll start with the left. So on the left, what we do? Well, we take each interval and we pick the left-hand point. So that will be the function at 0 times the width plus the function at 1 times the width. For the midpoint, what we do is we always choose the center point. So halfway between 0 and 1 is very conveniently a half. Halfway between 1 and 2, well, 3 halves, also known as 1 1/2. So that would be f at a half times 1 plus f at 3 halves times 1. And finally, for the right endpoint, well, we pick the one on the right. So we're going to go in this direction here. All right. Well, what is that going to be? Well, so it's going to be for the first interval, we're going to pick 1 times the width, plus the second interval, we're going to pick 2 times the width. All right. Now, from here, we need to do some evaluation. So let's do that. All right. F of 0, plug in 0. So we're plugging 0 in. This is our function, 34 over 1 plus x to the 4th. So this is where we plug things in. So here's our function, f of x. So when we plug in 0, that's easy. 34 over 1. So this is 34 plus f at 1. Well, 34 over 1 plus 1. That's 34 over 2. That's 17. All right. Here, by the way, is also f of 1. And we'll come back and talk about that in a second, the fact that they share something. And then f of 2. Well, 2 to the 4th is 16 plus 1 is 17. That's 17 downstairs. So 34 divided by 17 is 2. So 34 plus 17 makes this 51. 17 plus 2 makes this 19. Now these are a little bit harder to evaluate because they're fractions, and we have to take it to the fourth power. So for instance, if you plug in a half, what would you get? Well, you would get 34 over 1 plus 1 over 16. And here, if you plugged it in, you get 34 over 1 plus, now upstairs 3 to the fourth, turns out to be 81, downstairs is 16. These don't really simplify that great. They simplify a little bit, but again, not much. 34 over 1 plus 1 over 16, which is the same as 34 over 17 sixteenths, but I can flip it over, 16 seventeenths, and then you can take that, and lo and behold, you get 32. All right, well, that's not so bad. But let's try this one. This would be what? It would be 34, and downstairs you'd get 16 plus 81, which is 97, over 16. And if you flip it over, you'll get 16 over 97. And now these don't cancel. Ugh. All right. Well, now you see something. Look, these are complicated. These are complicated. And you're not going to be able to push very far because numerical integration involves lots of computation, especially if you have a function, which is why computers love it. Computers love numerical integration. They think it's the bee's knees. They love doing it. Whereas differentiation hates it. It thinks differentiation is a silly thing and is upset if you ask it to do something about our function. Now, on a side note, let's see, I do have it written down here in a second. We're going to refer back to it later on. If you do simplify the midpoint, what does that turn out to be? Well, it turns out to be, here we go, this is about 37.6. So we have three estimates. These are three approximations. Between the three of them, you might be thinking, 37.6 looks a little bit more reasonable. And as a rule of thumb, the midpoint does tend to do better. But keep in mind that does not say the midpoint is always best. It just, generally speaking, it tends to do better. So be careful. You shouldn't always think of going into saying it's like, what's the best routine for this set of data? Because you don't know. It just depends a little bit on the structure of the data. But what's the best routine in general? And that's what we're really after. All right, so Riemann sums, review from what we did in Calc 1. We have left, right, and center. All right, almost sounds like a politics broadcast, doesn't it? Left, right, and center. But what's the idea? Well, again, the idea is approximate it by nice rectangles. But we can do better. So here's the better. Instead of approximating each strip as a rectangle, let's go back to our shape we talked about before, which is a trapezoid. All right, what does that mean? Well, that means instead of thinking of the top as a flat function, or constant, we can have it be a line. So we're going to have it be a line. So what we do is we say, all right, the area is, we take 1/2, the height on the left and the height on the right. So h1 plus h2, and then times it by our width. And so our area is approximately 1/2 f of xk plus f of xk plus 1 times xk plus 1 minus xk. And what do we get? All right, well, we get an estimate. Now, here's something to think about. If I cover up the f of xk plus 1 term, I see the point on the left times the width. If I cover up the f of xk term, I get the point on the right times the width. In other words, I'm getting either the left hand or the right hand. So I can really break it up and say, oh, it's like I have the left and the right, then times 1/2. So I can think of the trapezoid as somehow being an average of the left hand and the right hand rule. So that's what we can think of. All right. Another thing to note is to sort of think about, all right, the top is a linear function. If you come back here, we have a constant function. Now here's the thing about a constant function. If you have a constant, you have 1 degree of freedom. So your 1 degree of freedom comes from your height. What is the height? When you have a linear function, you need 2 degrees of freedom. So your 2 degrees of freedom are, you're saying, I'm using information about those 2 points. What's happening at these 2 to help me understand what's happening on the interval. So that sort of feels like we're getting more information. And so since we're using more information, it should be a better estimate. And it is a better estimate. So here we go. Use the trapezoid rule with 2 strips of equal width to approximate this. Well, we could go through the argument. I'm going to skip it because I have this little piece here that the trapezoid rule says it's 1/2 the left estimate plus the right estimate, because I have already computed these. So I'm just going to recopy them. So the left, you can go back and check, it's 51, and the right, it's 19. 51 plus 19 is 70, divided by 2 makes 35. All right, so that's an estimate. It's an approximation. I want to go through and note something here. If we did do our trapezoid rule with 2, we would split it in part, and what would happen is in the first interval, I would take a look at this point at 1, thinking of it as my contribution from the right-hand side. And from the second interval, I would look at this interval and say, well, what's that contribution from the left hand? So in other words, what ends up happening is I'm going to look at this piece twice. But on the ends, I'm only going to see those once. So if you were to take this, one way that this is often written is we think of this xk plus 1 minus xk. We'll think of that as our width of our interval. So we'll call it delta. So we have our delta and over 2. So I'm going to write this as delta over 2. And now we say, all right, what's our contribution? Well, we have our initial point. Oftentimes we call that our x naught, our 0 point. Then we have our next point, which gets counted twice. So 2fx1. And all the points in the middle keep getting counted twice. So it's always 2, 2, 2. Up until the very near the end where 2f, the penultimate point, and then the last point only gets counted once. So what's the pattern? You have your delta, which is the width of your interval, divided by 2. And now if you read off the coefficients here, you'll see it's a 1, 2, 2, 2, 2, 1. So these aren't minuses, these are dashes. So 1, 2, 2, 2, 2, 2, 2, 1. Which means that in essence you're saying, look, the points on the end get weighed a little bit less than the points in the middle get weighed essentially equally. Now there's sort of a clue I like to note that helps me remember this, which is this 2 here. If you look at it, most of the time it's basically saying each point contributes 2. Or I should say, when I say it contributes 2, it contributes 2 times its height, on average. So, on average. So I need to compensate for this 2 times with this divided by 2. So that's where I can think of that 2 as coming from. So philosophically, it was saying if we were sampling our data, so here's our sampling points, saying that the ones on the end are a little bit less important than the ones in the middle. That's what's happening with the trapezoid rule. The 2 extreme ends, less important, the ones in the middle, more important. Okay. So we have rectangles, Riemann sums, we have trapezoid, we have lines. So the question is, what comes next? Okay. Whew. All right. Great question. Great question. And the answer is we think about what's the natural thing. We went from a constant function to a line. So the next natural thing, well, maybe natural, is a parabola. So this is called Simpson's rule. And so how does it work? Well, we have to be a little bit careful here. And I will say there's two perspectives about Simpson's rule. And I'm going to follow the one in the book, not the one I agree with. But okay, so the Simpson's rule says I want to approximate the top by a parabola. Now if you think about a parabola has three coefficients because you have like ax squared plus bx plus c, which means you have 3 degrees of freedom. That means I need 3 pieces of information. So where are our 3 pieces of information? Well, we're going to think of it as what's happening on the left, and on the right, and on the center. So that would be our 3 pieces of information. Now here's how the Simpson's rule works in practice. So to get a left, right, and center, instead of doing it as one interval that's split into 3 parts, we're really going to think of it as 2 intervals. So this dotted line is not the midpoint, it's xk plus 1. So I have xk to xk plus 1 and xk plus 1 to xk plus 2. So I'm gluing 2 strips together, and now I'm going to put one parabola on top of those 2 thin strips. All right, so in particular what I'm saying is once you tell me where these 3 points are, there is a unique parabola that goes through those 3 points. Now it's kind of hard to see here, so we've taken this picture and we've enlarged. We've embiggened, if you will. And so this is just, literally it's just the top of this picture blown up. Just to show you how much better we are. Because it's the same curve that we've been using for our other examples. But whereas in our other examples you can see there were definite gaps. So you go back to the trapezoid, you can see like, yeah, I'm missing a non-trivial chunk. Here, it's hard to see, even when you zoom in. So right here in the bottom, you see, okay, there's a little bit that we undercounted, like we missed that part. And here's a little bit that we're sort of like overcounting, but again, not by much. That's very small, our error. And it should be. The more information we use, the smaller our error should be. All right, so we have that the area under the parabola that passes through the left, the midpoint, and endpoint, we should really call this the right point. But we have that parabola, the area is 1/6 times what happens over here at f of xk, plus 4 times f of xk plus 1, plus what happens at f of xk plus 2. And then times by the width, xk plus 2 minus xk. So one of the ways you can think of it is like, well, we're really sampling. We take the points, but now we say, okay, you have the left, the right, but notice the midpoint. Wow, 4. That says the midpoint, that's worth a lot. The midpoint has better information about what's happening. And that seems reasonable. It seems like the midpoint should be better at capturing the behavior. Now, let's be careful here. This xk plus 2 minus xk, that's the whole way across. So really, in terms of what we've been thinking about before, see, our delta is just one interval. So when I look at this piece right here, it's really twice delta. So you got to be careful there. And so if you take the 2 into 6, you'll see that you'll get 1/3. So that's where this 1/3 comes from. Okay, so here we go. How do we do it? Well, we take our set of points, and here's the key. Is Simpson's rule says you have to break it into an even number of strips. So n has to be an even number. So I can't do 7 strips or 19 strips, but I can do 8, I can do 20. I need an even number. It's not as big a restriction as you think. I can just do a little bit of an approximation on the end to make it an even number. So what we get is we get the b minus a over 3n. Now, b minus a over n, this is just another name for delta. Okay, so that's good. And then the 2 and the 6, that's where that 3 comes from. So we should think of this really as this piece right here. We can think of this as being delta over 3. So whereas in the trapezoid rule, if you went back there, it was delta over 2. And if you went all the way back here, what you had is that this was just delta. So we went to delta over 2, and now we're at delta over 3. And probably like, ooh, next one is going to be delta over 4. Actually, this will be the last one. We're not going to push it much further. All right, so there we have that. So use Simpson's rule with 4 strips of equal width to approximate this integral. All right, so let's actually work through this. So I want to really get a good sense. So we're going to break it up into 4 pieces. 1, here's a half, here's 3 halves. And what do? Well, we're going to say that these 2 pieces, we're going to put a parabola on top of that. And what will the parabola look like? Well, we're going to have our delta over 3. So b minus a over 3n. So what is our delta? Well, let's be careful here. B minus a, that's 2 minus 0. So that's 2. Downstairs, we're going to have 3 times 4. All right, so 2 over 3 times 4, which would give us what? Well, the 2, 1/6. All right, 1/6. Good. So we are going to have 1/6. That's our leading coefficient. And then we're going to do what? Well, the rule says we're going to take our left hand, which is f of x0, plus 4 times the joining where the 2 strips combine. So plus 4, x0 is just 0, plus 4 f of 1/2 plus the right end. Okay, so that's going to be f of 1. Okay, that's going to be my first one, kind of. All right. All right. Yes? Good. Plus, and now we come here to the next one. We take the left hand, so that's f of 1 plus 4 times f of 3/2 plus f of 2. Now, what I want to point out here is we have something similar to what was happening with the trapezoid rule. Namely, that when we look at 2 consecutive pairs, they combine together. So what we really end up with is 1/6 times f of 0 plus 4f of 1/2 plus 2f of 1 plus 4f of 3/2 plus f of 2. Figure out what that is. Life is good. Now, it might seem that there's a pattern here, and there is a pattern. So what we have is that these are the coefficients 1, 4, 2, and they're just going to keep alternating. So it goes 1, 4, 2, 4, 2, 4, 2, dot, 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 and at the second to the last one are 2, well, wait, hold on a second. 2, 4, 1. There we go. There's our pattern. So that's the pattern to remember for the coefficients. 1, 4, 2, 4, 2, 4, 2, da, 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 1. Good. Now, all right, what can we say? A couple of interesting things to note. And this seems strange, but we know the theory says it's actually good. If you look at where the 4s are, it's like every other. So what it's saying is, if you take your data, so let's say this is our data. If you have an even number of strips, that ends up being an odd number of points. So this is your x0, here's your xn. And then what we're saying is that the points here, these interleaving points, are somehow more important. We put more weight than these points over here. And if you do that, you'll get a better estimate. Okay, well that's interesting. Not so obvious. So in essence, what we've been doing as we've talked about these different things is we're sampling our data and we're saying, okay, as you weight the sampled data, how do you do it in a way that gives you a better result? And so this says you don't treat all the data the same. You do a little bit of altering, and then you get a better approximation. And life is good. Now at this point, you're probably thinking, we have to work through this. And the answer is, actually, we can save ourselves a little bit of work. Because what? Well, we can think of this as sort of a couple pieces together. We can think of this as there's f of 0 and f of 1 is really like the left hand. F of 1 and f of 2 is really like the right hand. F of a half and f of 3 halves times 4 is like the midpoint for two strips. So that's what we mean here when we say the Simpson's rule. It's like averaging left and right in the midpoint. So what we can do is we can just write down our answer from before, just appropriately weight everything. So if we do that, I'm going to refer to my notes here as I do that to make sure I get it right. We get that our approximation is we take 1/6, what we got from the left, which is 51, plus 4 times what we got from the right, which is 37.6, plus what we got from the left, which is 19. And you might say, wait a second, hold on. These were with 2 strips, and this is with 4 strips. And the answer is, yes, you're absolutely right. That's the way it works. Because 2 strips together are forming a piece that we put a parabola on top of. That's why we have that phenomenon going on. If you were to go through and clean this all up, you would get the following. 36.7 something, something, something. All right. So how did we do? We have all these different estimates. We're putting them all together. How do they all compare? For instance, could we actually compute them? And the answer is that yes, it is computable because it's actually something we have tools for. It just would take us a long time. So the actual value of the integral from 0 to 2 of 34 over 1 plus x to the 4th is equal, naturally, to this expression. 17 over 2 root 2 times 2 pi plus log of some crazy expression minus 2 arctangent of some unusual value, which is 36.384. Now we talked about several estimates. We have our constant estimates where we put what's on the top is a constant function. So you have the left, the right, and the midpoint, and these are the values that come out, 15, 19, 37.608. They're kind of all over the map. The trapezoid, which is you put a line on the top, is 35. That's pretty close. That's not so far off. It's about not so far off again from the midpoint. But the quadratic, that's actually even better than all the rest, right? 36.738. We're off by 0.3 something, I think, 0.35. That's a very small error. And now, what's the idea? Well, generally, the further down you go here, the better your estimate gets. Because the further down you go, you're more closely approximating what you think a function should do. Functions are more like lines than they're like constants, and they're also more like parabolas than they are like lines. Now, you might say, could we keep going down this list? And you could absolutely make up more and more functions to look at. I don't know if they'd get you a lot more information, but certainly you could go further down the list. All right, let's do one example and see what we get. All right, use all the methods discussed with 4 intervals of equal width to approximate the integral from 0 to 4 of x to the 4th. All right, well, let's see what we get. All right, 4 intervals. So, well, all right, so the left, that's not so bad. So we're thinking of x to the 4th. This is our function f of x. And what would we have? Well, our delta is equal to 1 because we went from 0 to 4. Divide that by 4. That would give us width 1 for each piece. Now be careful. We know we have lots of examples with delta equals 1. So on things like quizzes or exams, we might change it to delta equals 2 or delta equals a half, just to see if you remember to put it in there. But of course you would. You're a good student. You do great. So the left hand, you have your delta in front, and then you take your left endpoints, f of 0 plus f of 1 plus f of, there's an extra parenthesis there, plus f of 2. And whatever that turned out to be, I'll skip the computation. I just want to go through and see what these look like. For the right, you'd have your delta, and then you take your f of, wait a second, hold on. You can't, I can't believe I missed this, plus f of 3. There we go. Because if we have 4 intervals, we better have 4 terms for our Riemann sum. I'm sorry about that. Okay, right endpoints are going to be 1, 2, 3, 4. So f of 1 plus f of 2 plus f of 3 plus f of 4. Okay, and that turns out to be something, and you can compute that. The midpoint, well, that's your width delta, and then it would be what's halfway between 0 and 1. Well, that's the function at a half. Whatever that turns out to be, a half to the 4th, that's like 16th. Then the next one, halfway between 1 and 2, is 3 halves. Okay, that gets more interesting. That would be 81 over 16. Next one, f of 5 over 2. Oh, all right, now raise that to the 4th power. That's 625 over 16. F of 7 halves. Raise that to the 4th power. Well, okay, go grab your calculator. That's what you'll need. Yeah. Actually, it's kind of interesting. 343 is 7 cubed. And it's a nice number, right? 343. It just rolls off the tongue when you think about it. And so if you take 343 times 7, that would be 2100 plus another 280. That's 2380 plus another 21. So 2201? Is that? Anyways, it's not so bad. You can compute it. Okay, so these are our constants if we approximate the top by something flat and unchanging. So the next level up was the trapezoid rule. Now, how does the trapezoid work? Well, you take your delta over 2. So in this case, it'd be a half. And then remember the pattern. It says that the 2 extreme ends are not as valuable as the points in the middle. So that says we're going to take f of 0 plus 2f of 1 plus 2f of 2 plus 2f of 3 plus f of 4. So again, the f of 0 and f of 4 are basically half as valuable as the information in the middle. So that's if we approximate the top by a line. And finally, our Simpson's rule. Okay, so how does Simpson's rule work? Well, we're going to take delta over 3, 1/3. And how does that proceed? Well, remember the pattern. It's going to be 1, the endpoint. Then the next point will be worth 4. Okay, so that's 4, f of 1. Then the next one is worth 2. Not because it's 2, it's just the pattern. 1, 4, 2, 4, keeps it going. Then the next point is worth 3. 4, f of 3. And then we'll get to the end point, and that's just worth 1 again. Now, one thing I want to point out is, look at this 2. In essence, every time we're like adding twice something, except for maybe the ends. So on average, it's like 2 times something, so divided by 2. For Simpson's rule, well, it's alternates between 4 and 2. Don't worry about the ends. They take care of themselves. So if half the time I'm adding 4 and half the time I'm adding 2, approximately on average, it's like I'm scaling up by 3, so I need to scale down by 3 as well. And there you go. So that would be what they would turn out to be if you were to go through and run the computation. None of them are too bad other than the midpoint. The midpoint, that does not look pleasant. And because that's not going to be pleasant, we'll go ahead and skip the computation, leave it as an exercise to the reader, right? Okay, that's just another way of saying, yeah, it's not the most fun. And numerical integration, like I said, computers love it. Humans, they don't love it very much if they have to do much by hand. It's definitely not something you want to do if you only have coconuts on a desert island. You want to find better ways to approximate things. And in the last part of the course, we will get into a method where when we do have some of these more exotic functions, we see that we can approximate things in a nice way by polynomials. But that's coming up at the very end. All right, you've been patient, and if you got all the way to this part in the video, let's just quickly talk about why does Simpson's rule work? because it doesn't seem like a totally obvious thing as how it would go about. You need a couple of facts. A squared minus b squared is a plus b times a minus b. That's pretty well known. And a cubed minus b cubed also factors in a nice way. A squared plus ab plus b squared times a minus b. The fact that you both see a minus b in these is going to be important. So suppose we have our parabola. Ax squared plus bx plus c for some choice of a, b, and c. I don't know what a, b, and c are, and here's the beautiful thing. We actually don't have to solve for it. By the end of the process, we'll just say, oh, whatever a, b, and c are, it just works out the right way, regardless. So the first thing we're going to do is we're going to figure out, well, what's the area? So we're going between xk to xk plus 2 of our parabola. So we just do the integral. That's 1/3 ax cubed plus 1/2 bx squared plus c times x. We plug in our xk plus 2 and our xk. So it's 1/3 a xk plus 2 cubed minus xk cubed. 1/2 b xk plus 2 squared minus xk squared. And then c xk plus 2 and xk. So we're going to call our delta x, that's xk plus 2 minus xk. See how there's a delta x here? But there's also going to be a delta x here because of difference of squares. And there's also going to be a delta x there because of difference of squares. So you pull it out. And when you do, you're going to be left with 1/3 times a times this expression plus 1/2 times b times that expression plus c. All right. Now the other thing to note is if I have f of xk and I plug it in, I get that expression. If I have f of xk plus 2 and plug it in again, that's what I would get. And if I plugged in the midpoint, well, halfway between the xk and xk plus 2 is xk plus 1. So xk plus 1 is 1/2 of these two. And if you plug it in and you work it out, you get that expression. No big surprise. So now what we're going to do is we're going to take some combination of these. And the trick is, here's sort of where it sort of just pops out of the blue as to which combination do we take. You can, by doing some not very hard manipulation, figure out what the right combination is. But for now, let's just go on faith that the combination we want is one of the ones on the left, 4 times the one in the middle, and 1 for the point on the right. Okay? All right. So we're going to take one of these, 4 of these, and 1 of those. And I'm just taking this information, scaling as appropriate, and adding them together. And when we do that, well, what's in front of the a? Well, you've got a couple things. You've got an xk squared, which is good. And you've got an xk plus 2 squared. And then you got another xk squared, another xk plus 2 squared. So that's where that 2 is coming from. And you have the cross term, which is 2 times xk plus 2xk, which also comes out. Okay, so that's just the a term. Similar for the b term. You've got b times xk. Well, here's another 2b times xk, so that gives us 3b times xk. And similar, there's a 3b xk plus 2. C, 4c, and c is 6c. Now, the key here is to say, stare at this expression and stare at that expression. And then if you stare for a while, you're going to be like, oh, these are really similar. Very similar. How so? Well, if you were to multiply this by 6, you'd get 2a times that. Here you'd get 3b times that, and here you get 6c. So these are essentially the same up to the factor of 6 and this little delta x. So now we say, hey, that means this is the area times this part. Now we're just going to take this stuff and move it over to that side. So we get that the area, well, the xk plus 2 minus xk, and the 1 6, so that's where those come from. And then you have that part right there. And it works out beautifully. You never need to know what a, b, and c are. They just work out. Wow, that's amazing. Amazing. And you know, there's something even more amazing. Simpson's rule is not just good for parabolas. It turns out it's really good for cubics. Amazingly good. So, life is nice. So that's it. All right. Well, where are we going? Next time we're going to revisit Simpson's rule and trapezoid rule and remind ourselves that, look, an estimate is only as good as its error. So we're going to talk about what can we say about our error. Because if we know our error is small, we have confidence in our estimate and we feel good. If we don't, we'll never know. We might lose confidence. So that's where we're going next time. So come back and have a good day. Bye.